Yes, oh yes, it's Uncle Jegs, and today's video is all about the temperature change required practical. To understand this, we have to first go through the theory of energy changes, then we'll look at the required practical itself, and then finally, I'll look at a question that requires you to make some improvements to the experiment. As always, check the description for the worksheet and also the answers to the previous video's worksheet. Alright, let's geek that. Man like Carl Sagan once said, if you wish to make an apple pie from scratch, you must first invent the universe. This sentence perfectly captures one of the big ideas in chemistry, the law of conservation of energy. This just means that energy is never created or destroyed. If you deep it, that means that the total energy in the universe has not changed since the Big Bang. It has just transferred from one part of the universe to another. When a chemical reaction happens, there are two locations that the energy can move between: the reaction and the surroundings. Everything that isn't in your beaker or the test tube is your surrounding. The air is the surrounding, the walls the surroundings, your do-rag is the surrounding as well. You get the idea. We classify reactions based on whether they release energy into the surroundings or if they take energy from the surroundings. Reactions that release energy into the surroundings are called exothermic because heat energy is exiting into the surroundings. And remember that the surroundings includes your hand and the thermometer. So this heat energy is being absorbed into the thermometer and into your hand to make the reaction feel hotter. Reactions that absorb energy from the surroundings are called endothermic reactions. Since this heat energy will be absorbed from everything around the reaction vessel, your hand, the thermometer, everything will feel cooler.
What? How does that even make sense?
What you mean?
If something is absorbing energy from the surroundings, shouldn't it feel hotter rather than cooler?
That's an excellent point. To help you think about this, I'll draw an analogy between when you're holding an ice cream. How does it feel when you hold it?
Cold, innit?
And now think, what happens after a while if you keep holding it?
I'll yam it still.
No, I mean, if you don't eat it, what would happen?
It melts?
Exactly, it melts. And why does it melt exactly?
My hands warmed it up.
You transferred energy into the ice cream. Even though it feels cold, it's actually gaining energy. This isn't a perfect analogy, but let's just run with it for now, okay? During an endothermic reaction, energy is taken from the surroundings to turn your reactants into products. That means that energy that was once in the surrounding has been locked up in our product. That means that the particles in the surroundings are now moving slower. They have less kinetic energy. Since your hand and the thermometer are also part of the surroundings, they will be measuring the slower moving particles. We can plot this change in energy on a reaction profile. Energy is on our y-axis and time or progress of reaction goes on your x-axis. The reactants have a certain amount of energy, but then energy is absorbed as the reaction happens. So the products have more energy than the reactants. In reality, there is actually a little bit of energy that must be absorbed for the reaction to get going. This energy is called the activation energy, and we measure it from the reactants to the top over here. And of course, the opposite is true for exothermic reactions. These release energy into the surroundings, which means that the particles in the surroundings gain more kinetic energy. This means that a thermometer will read this as an increase in thermal energy. It feels warmer. The reaction profile for an exothermic reaction, since they lose energy, should have the products lower than the reactants. They have less energy. They will also have an activation energy as well, and that looks something like this structure over here. It's time for the reaction. You will investigate the different variables that affect energy changes in solutions. In this example, I'll be reacting hydrochloric acid and sodium hydroxide. The independent variable here would be the volume of sodium hydroxide. Look at this table and you can see that I will be going from 0 centimeters cubed to 40 centimeters cubed of our sodium hydroxide solution. Therefore, the dependent variable would be the temperature of the solution. First thing we do is that we add a measured amount of dilute hydrochloric acid to a polystyrene cup. You should then put this in a beaker. This has nothing to do with the heat, but just to keep the cup more stable. Before you add your second reactant, make sure you measure the start temperature. This will be recorded in your 0 centimeters cubed part of your table. Then you add out the 5 centimeters cubed of your sodium hydroxide. Pour it in and put the lid on the cup. Your cup lid should also have a hole in it where your thermometer can stick out through, so you can monitor the temperature as the reaction goes on. When the temperature stops rising, you record this temperature and repeat with the different volumes of sodium hydroxide. After you've done your final test, you do it again. This is so you can work out a mean. Look at this question. It links reactivity series, displacement reaction, and temperature change. Some students investigated the reactivity of 4 unknown metals, W, X, Y, and Z. These letters don't stand for the symbols of the elements. The student used the metal salt solutions of copper nitrate, magnesium sulfate, and zinc chloride. This is the method used. First, they pour a solution of the metal salt into a glass beaker. They measure the temperature of the solution. They add 1 gram of the metal to the solution. They measure the temperature of the solution, and then they calculate the temperature increase. There are 4 important improvements that we can make for this method. The first thing is that we pour a measured amount of the solution and into a polystyrene cup. Remember, we're trying to reduce that heat loss. Then we can stir the solution as well when we've added our metal. Just make sure everything's evenly mixed. Then we record the highest temperature, or if it's an endothermic reaction, the lowest temperature. And finally, you do it again. You repeat the experiment so that you can work out the mean. And that, ladies and gentlemen, was the temperature change required practical. You already know what to do. Get the worksheet from below and also the answers to the previous video's worksheet. Like if you like, hit the notification bell to get these videos when they drop. See you in a bit.